Okay, here we go. Lesson 104. So in this lesson, we're going to talk about the scalar product and its property. So we'll first look at the geometrical property of scalar product. So consider we have two vectors u and v, and they are arranged in a tail-to-tail configuration. So the angle between the two vectors is theta. Then we can find the scalar or dot product of u dot v by multiplying the magnitude of the two vectors and then times that by cosine theta. The result, please note, of a scalar product or a dot product is always a scalar. In physics, the application of a scalar product is really to calculate the work done by a force over displacement, delta D, okay, so to speak. But we're just going to look at the property of scalar products from a mathematical standpoint for now. So let's consider then, what if we have two perpendicular vectors, u and v, as shown in the first diagram? Let's try to find the scalar product using the geometrical properties. So we can say that u dot v is equal to the magnitude of u times the magnitude of v cosine, in this case, 90 degrees or pi over 2. As you know, cosine 90 is equal to 0. This tells us that the dot product between two vectors or non-zero vectors that are perpendicular to each other must be 0. This is a useful property when we need to solve vector questions. Okay? Now, what if I have a vector A and I want to find A dot A? Here I have vector A magnitude times itself, cosine, the angle between two vectors A's would be 0 degrees or 0 radians, doesn't matter. Cosine 0 is equal to 1. So this turns out if I take the dot product of a vector by itself, I'm going to get the square of its magnitude. Okay, another very important property. What if now we try to dot a unit vector instead? So b hat here. Well, similar to a dot a, I already know that if I dot b and b, I'm going to get the magnitude of the unit vector squared. But then we know that because this is unit vector, its magnitude is 1. So 1 squared is 1. So another special property, which is when you dot a unit vector by itself, you always get 1. So below here, we have a list of properties of the dot product. So note that, first of all, dot product is commutative. It also follows distributive and associative properties, meaning that you can switch the order of u dot v and v dot u. They're the same. When you have u dot, the resultant of v plus w vectors is the same as finding the sum of the dot products u dot v plus u dot w, kind of like the distributive property. What you should know or notice here is that when I add two vectors together, I do get a vector property or a vector quantity, and then here, so I have a vector dot vector. But then when I do the dot products, this is a scalar. This is also a scalar, which doesn't go against the idea of vector dot vector, is a scalar result. Okay? An associative property simply means that, if you have a scalar multiple of, let's say, vector u, dot v is the same as calculating u dot kv, which is the same as multiplying the scalar vector k to the result of u dot v. What about magnitudes? Well, we just saw this, so let's write this out again. Vector u dot u is always a square of the magnitude of u. U hat dot u hat, so these are unit vectors, we always get 1. Something to note about the cosine theta in the geometric interpretation of the scalar product. The value of cosine theta when theta is 90 degrees We saw that, well, A dot B would be 0 because cosine 90 is 0. If theta is an acute angle between 0 to 90, then A dot B, if you notice the function of y equals to cos theta, well, we will always get a positive dot product. Make sense? But if we have theta being an obtuse angle between 90 to 180 degrees, then the dot product must be negative, as the value of cosine theta of these angles will be negative. Let's take a look at example 1. Given the unit vectors I, j, k in 3 space, complete the following. Oh, the k hat went somewhere else. K should be here. Weird. Okay, let's see. Why don't you try this? I, j, k, these are the standard basis vectors. So I dot I is 1. J dot j is 1. K dot k is 1. How about I dot j? The angle between vector I and j is a 90 degree, right? Because this is the x-axis, y-axis, and z-axis. As a result, we know that any vectors that are perpendicular to each other will have a scalar product of 0. I dot k, once again, perpendicular. J dot k, perpendicular. So all zeros. Example 2. Calculate the dot product given that the magnitude of vector u is 3, magnitude of v is 5, and theta between the two vectors is 30 degrees. Like you see here, this is simply testing out or working out the dot product of the two vectors using the formula. It's very, very important to note that you use a dot to represent the dot product. If you write something like uv with nothing in between it, this has no meaning. Because after all, the dot product is a reserved symbol or notation, is a real operation between vectors, okay? And later on, we're also going to look at something called a cross product, which gives you a vector quantity, okay? Save that for later. Okay, going back to the question. So I know that the dot product is basically magnitude of u, magnitude of v times cosine theta. So let's sub 3 times 5 times cosine 30 degrees. And if it helps, 2, 1, root 3, 30 degrees is here. So cos 30 is root 3 over 2. That means I have 15 root 3 over 2. That's it. And yes, we do get a scalar quantity as a result. Let's take a look at example 3. So here we're given magnitude of A, magnitude of B, and also the dot product, A dot B, equaling negative 12. We want to find the exact value of cosine theta. Before we carry out our calculation, you should use the given information as a hint to judge how valid your final answer will be. Notice how A dot B is a negative value. It suggests that, well, because magnitude cannot be negative, we are really dealing with an obtuse angle between the two vectors A and B. We're not finding the angle here, we're just finding cosine, but that's something, important to note when you're dealing with dot products. Okay, so we know that A dot B is equal to the magnitude of A times the magnitude of B times cosine theta. Since I'm looking for theta, I'm going to rearrange this formula. So cos theta is equal to A dot B over the product of the magnitude, of the two vectors. And you may want to write this down. This is a handy formula for finding the angle, really, between two vectors. Okay, we will see this a lot in later lessons. Okay, carrying on. So negative 1 to 12, and then 3 times 8, that's 24. Therefore, the value of cosine theta here is negative 1 over 2. Okay, that's it. So far we're just like practicing how to apply the formula for dot product if we are working with geometric vectors. Next, we know that we can work with algebraic vectors too, which is a time when vectors are represented using, the endpoint, so to speak. If they're position vectors, the endpoint from origin to the endpoint, the terminal point of those vectors. Okay, and algebraic form, we list them. We list out the x, y, z or x, y components in 2 space or x, y, z components of a vector in 3 space. All right. So let's compare. In the chart, I'm comparing the dot product calculations for geometric form, which we just saw, to algebraic form. If I have 2 algebraic vectors a and b, we indicate the x components using subscript 1, y components using subscript 2, and z components using subscript 3. You notice that the algebraic form of a dot b really is to multiply, right, the x components of the 2 vectors plus the y components of the 2 vectors plus the z components, multiply together to get that. Okay, and then if you sub in this expression into the calculation of cosine theta, then you replace a dot b with a1b1 plus a2b2 plus a3b3 over the magnitude of a times the magnitude of b, just like that. Okay, so now let's calculate the dot product of 2 vectors in 2 space, u and v. U dot v is equal to x1 times x2 plus y1 times y2. Okay, just like that. So 4 times 2 is 8 minus 15, that's negative 7. Okay. Next, we have vectors m and n in 3 space. So following the same idea, m dot n would be 3 times negative 2 plus negative 2 times 5 plus negative 5 times negative 7. We have negative 6 minus 10 plus 35. So 25 minus 6, 19. Okay. Still with the same pairs of vectors in example 5, let's find the angle theta between these vector pairs. So using the cosine theta version of dot product, we know that cos theta is u dot v over magnitude of u times magnitude of b. So we calculated the dot product to be negative 7 in example 4. Now let's find the magnitude. So let's square 4, 16 plus square 3, 9 times 4 plus 25. Here we have negative 7 over square root of 25 is 5. And then 4, so square root of 29 here. To find theta, we need to take arc cos of this ratio. Take the arc cos of this ratio, we get 105 degrees. If I round this to 3 significant figures. Okay. So similarly, in 3 space, we have cos theta equals to m dot n over magnitude of m times magnitude of n. The dot product is 19. How about the magnitude? We have 3 squared, 2 squared, 5 squared for m, and then 2 squared, 5 squared, 7 squared for n. This is all over What have we got here? We have 9, 4 is 13, so 38. And then we have 29, 678. Okay, so 19 at the top here. Arc cos of that whole mess is 69.6 degrees when you round it to 3 significant figures. All right. Here we have example 6. If vectors A and B are unit vectors and the angle between them is 60 degrees, calculate 7a minus b dot 3a plus b. All right, so we can, try to use distributive properties to work out this dot product first before we try to substitute anything into the expression. So let me rewrite the question. All right. So knowing how vectors work very similar to polynomials, let's expand. So here, the catch is that when I expand this using distributive property, I'm not multiplying. I am dotting, so to speak. Okay, I'm still retaining a scalar product. So 7a dot 3a is 21a dot a. If you don't show the dot product, you do not get the correct mark because it means nothing without a dot. Okay. Next, I have plus 7a dot b minus b dot 3a and then minus b dot b. Here I know that 21a dot a is the magnitude of a squared minus, let's do b dot b first. So this is magnitude of b squared plus 7a dot b. I'm going to apply the property, the commutative property. So b dot 3a is the same as minus 3a dot b. Okay? And so magnitude of a is equal to magnitude of b because these are unit vectors. They're both 1. So here I really have 21 minus 1 plus 7 a dot b minus 3a dot b is 4a dot b, which is 20 plus 4. And now let's, apply the formula to calculate a dot b. So magnitude of a, magnitude of b cosine, angle between them is 60 degrees. So this is 4 times 1 times 1 times cos 60 is 1/2. So this is 22. Okay. So you may be wondering, can I skip step? Well, because you're applying the properties of dot products, theoretically speaking, you cannot skip any of these steps. You have to show which property you're using. Okay. Number 7. For what values of k are the following vectors perpendicular? So here we see a keyword perpendicular. And notice that we know some kind of property about perpendicular products and how that relates to a dot product, right? Because if vector A is perpendicular to vector B, then I know A dot B must equal to 0. Okay. So let's work out the dot product of vector A dot B. Multiplying the x components together, k times k squared, plus 2 times 1, 2, plus negative 3 times k, so minus 3k. I actually have a quadratic equation here. I think I can factor this. K, I need product of 2, sum of negative 3, so let's make those negative. And so the values of k should be 2 or 1. Okay. So last but not least, we have example 8. Determine the components of a vector that is perpendicular to both P and Q. So it sounds similar to example 7, but it's not really the same thing. In example 7, we know what those vectors are, right? We're just looking for K when we relate them together. In this question, we are actually dealing with a third vector that is perpendicular to both P and Q. So I'm going to just say let V to be the vector that I'm looking for, and V is A, B, and C, since I have no idea what the components are. Such that, so be a vector, such that vector P is perpendicular to vector V, and vector Q is also perpendicular to vector V. Okay? Hence, what can we say based on those relationships? I can say that when I find P dot V, it must be 0. And, when I find Q dot V, this is also equal to 0. Okay? So let's dot the two vectors. I'm going to use column vectors in this case, just for the fun of it. Okay, so here I have A plus 2B minus C equals to 0. Let's call this equation 1. Vector V, Q is -1, 0, and 2 dot A, B, C. And so I have negative A plus 0B plus 2C is equal to 0. I can rearrange this slightly and say that A is equal to 2C. Let's call this equation 2. I can substitute 2 into 1, which gives me 2C plus 2B minus C equals to 0. 2B minus plus C is equal to 0. B is negative C over 2. So you might be wondering, why did we write B in terms of C? Isn't it much easier to write C in terms of B? Well, the reason behind that is that I have already expressed A in terms of C. And we know that, this is going to be, we won't get one single vector that is perpendicular to P and Q, but rather we're going to find, a whole so-called family of vectors that would be perpendicular to both P and Q. Okay, so we can easily use a parameter for C and express the vector V using 2C, negative C over 2, and C. Okay, so as long as vector V follows this pattern, then it will be a vector that is perpendicular to both P and Q. Okay, and that's it.